Welcome to week 4 of Artificial Intelligence with JavaScript, and today we will be looking at the general topic of pathfinding, touching on the concept of heuristics. Pathfinding is a general term involving working your way from a start point on an interconnected network to a goal point somewhere else, traversing your way from point to point, or node to node if you prefer. It's map reading basically, but as on a real map, not every point is connected to every other. Also, the paths from one point to another have certain numbers associated with them. These numbers are sometimes termed weights or strengths, and they are used to rate how good or bad paths are. Take a look at these two paths. The total weight is 163 if you go via C, and 336 if you go via D. Now, which one of these is better depends on whether a high weight is good or bad. If that were a street map, and the weights represented distance travelled, we would want to minimise the weight of a path. If the points represented some state of some system, like a society or business for instance, and the weights represented a positive aspect like wealth, then we would want to maximise the weight of a path. These networks don't necessarily represent physical maps. They could represent things such as decisions to be made or something similar. Point A might represent the state of my life at the moment, and point B where I want to be in 5 years' time, sunning myself on a tropical island in my case. With all the other points, the different situations in between. If the weight values represent the different amounts of money I could earn by acting one way or another, then you bet I would want to maximise the total weight value from A to B. We can use the weights on different paths to indicate things like one-way streets on maps. If A and B are joined by a one-way street, which permits you to travel from B to A, but not the other way round, we can set a path from B to A, but not one from A to B. That might take the form of setting the distance from A to B to an arbitrarily large figure, such as 1,000,000, to indicate that no path from A to B exists. That's assuming that low weights are better than high ones, of course. If you wanted to maximise weight values, then a figure of -1,000,000, or billion, or whatever, would do the same thing. Effectively, it takes that path out of the running. The same would apply to planning the path for a wheeled robot that would find going upstairs considerably harder than going downstairs. The path upstairs has a high weight, but in the reverse direction the weight is low. Let's hope that there's a lift available somewhere on the network. Of course, the paths on the network don't have to have weights on them. You've almost certainly heard of the famous fox, rabbit and carrot problem, where a farmer has to transport a fox, a rabbit and a carrot across a river. But he can't leave the fox alone with the rabbit, or the rabbit alone with the carrot. However, he only has room in his boat for himself and one of the 3 objects. In this case, each path represents one journey across the river, with or without an object in the boat. The entire network is too extensive for one screen, but I have displayed part of it here. The main thing to note is the branches marked with a red cross. These represent dead ends in the network, either because the fox has been left alone with the rabbit and has eaten it, or the rabbit has been left alone with the carrot and has eaten it. The other type of dead end comprises paths that duplicate a previous situation. For example, one possible path has the farmer taking the fox across the river, then bringing it back, thus returning the network to the original position. However, there are no actual weights on the paths. The only thing that's important here is reaching the goal state of the farmer and the 3 objects safely on the other side of the river. If more than one solution were found, and there are 2 possible solutions to this problem, then the better one will be the path that involved fewer river crossings. So what would a general pathfinding algorithm look like? The approach is to take the start point and consider all possible paths to adjacent points. These form the start of a list of partial paths, together with the distances from the start to each of those jumping off points. These paths are partial in the sense that, with luck, they take us closer to the goal, but we're not there yet. Then take the first partial path from the front of the list and repeat the process on that. Expand it to all the points in the network that are one step away from the current end, with the restriction that it cannot double back on itself. Taking the path from A to C and expanding it cannot include a possible move back to A again. The running totals of the weights are updated for each of these new paths. The procedure is then repeated with the next partial path being removed from the top of the list, A to D in this case, and expanded to the neighbouring points, to form longer partial paths, which are then added to the end of the list. Looking at the network, you can see that this approach vaguely corresponds to a vertical line sweeping from left to right across the network, with all paths up to that line being investigated in parallel. We keep expanding and pushing that line to the right until we reach the real goal point, or we run out of paths because all possibles have been expanded as far as they can be with no success. Because we are spreading our attention along all possible paths at once, this approach is called a breadth-first approach. An alternative approach is depth-first, in which we take one initial path, say A to C, take one further step from C, say to H, and then expand one step from H and so on. We are following one path down as far as we can until we hit a dead end or reach the goal point. There's a great deal of backtracking as we hit one dead end after another and have to retrace our steps. Again, like the breadth-first approach, we forbid any point from appearing more than once in any path to prevent paths going round in circles. This is depth-first pathfinding. Going back to breadth-first, you will have noticed that we very soon have two possible routes from point A to point C, either directly or via D. It is possible to apply Dijkstras' algorithm, yes, that's how you pronounce that name, which evaluates the shortest distance to each of the intermediate points and uses those to prune available partial paths. The algorithm exists in several different forms, but in each case we expand the path with the shortest distance to any given node. So in the case of A to C, we pick the one with the best, be that lowest or highest as appropriate, distance, and remove the other one. There's no point expanding A to D to C if A direct to C is better. With Dijkstra's algorithm, every time we expand to a point on the graph, we check to see if we already have a better way of getting to that point. Of course, if the paths don't have weights on them, such as those in the fox, rabbit and carrot problem, Dijkstra's algorithm can't really help us. One variation on either breadth-first or depth-first pathfinding is to work on expanding two sets of paths simultaneously, firstly from the starting point towards the goal, as we've done up to now, but at the same time the partial paths from the goal working back towards the starting point. In this diagram, you can see the red line moving from left to right, with the partial paths discovered so far listed in red, and the blue line working the other way, with those partial paths listed in blue. Eventually, the two lines are bound to meet, and we will find points appearing in both the red list and the blue list. Suddenly, we will have listed all the possible paths to the network from start to finish, from which we can then pick the optimal one. This approach has been likened to digging the tunnel under the English Channel, with work progressing from both the English sides and the French side at the same time. The approach works best with breadth-first expansion, in which case the sets of partial paths will inevitably touch each other, assuming a through route exists. The real channel tunnel was built in a depth-first manner, only one tunnel from each end calculated to meet the other exactly. This wouldn't be particularly reliable in traversing a network, as the two depth-first partial paths might miss each other and pass by. This would be the equivalent of the French Channel Tunnel coming up in Dover at the same time that the English effort comes up in Calais. Of course, it might be argued that in this case you would get two channel tunnels for the price of one. Up to now, although we have found a way of making the search more efficient, we still have to expand essentially all the partial paths on the grid until we find the goal or hit a final dead end. We can take that one step further by applying a heuristic. A heuristic is basically a rule of thumb. It's an approach that we can use when faced with an exploding number of possibilities, to put them in some sort of order. Given lots of partial paths that we can expand, a heuristic will tell us which ones are more promising, so we can expand those first. Unlike Dijkstra's algorithm, it's not guaranteed to find the most efficient path from start to finish, and might not even find a path at all, even if one exists. But more often than not, a well-designed heuristic will drastically reduce the workload needed to find the path to the goal. That's all a bit vague, so let's make it clearer with an example. Suppose you're reading a map printed very small, so that you can only see it by looking through a magnifying glass. You know that you are travelling from the top left corner of the map to the bottom right, but the magnifying glass only shows part of the map. Judging by the tiny fraction of the map that we can see here, our best strategy seems to be to head towards the southeast, since it takes us closer to our goal as the crow flies. Given the information in front of us and nothing else, we would probably try heading south on Elgar Road. Of course, we might move the magnifying glass only to find that Elgar Road was a dead end, and we would have to backtrack and try a different route. But generally speaking, heading towards the southeast of the bit of the map we can see is a sensible strategy. One phrase you will hear when discussing heuristics is hill climbing. This idea comes from the notion of hill climbing in the real world. You want to get to the top of a hill, but unfortunately the visibility doesn't let you see where the top of the hill is. Perhaps there's a thick fog surrounding you, so that you can only see a few yards in any direction. The rule of thumb in this case is an obvious one: head uphill. Even with a restricted view, you can usually tell which direction is upwards. However, like the map heuristic, this approach is not guaranteed to succeed. One problem is that of a local maximum, or foothill. You reach what you think is the top of the mountain, and you plant your flag. Then the fog lifts, and you find to your embarrassment that you have reached the top of a small foothill, and that the real mountain is right next to you. This is caused by the fact that your heuristic can only see a certain distance in any direction. Another more subtle problem is traversing ridges. If your simple heuristic only measures the height of the terrain directly to your north, to your east, to your south, and to your west, then it's possible to climb onto a ridge travelling from the northwest to the southeast and think that you have reached the top of the hill. This is because the land falls away on each of those 4 points of the compass that you are measuring, and yet to the northwest or the southeast the land is just as high as the point you're standing on, maybe even higher. This problem can occur when you can only use crude measurements of the score that you are judging your heuristic by. Solutions do exist to both of these problems, such as simulated annealing, which I won't go into here, but even without them, the advantages that heuristics give generally outweigh the disadvantages. When used properly, heuristics are a very powerful tool, but they do have to be well designed and properly implemented, of course. That's the end of the lecture. To illustrate the concept of pathfinding, the JavaScript example implements a simple word puzzle, where you have to change one word into another one letter at a time. Each letter change is one further step through the network, with the individual points being possible words of the English language. I hope you enjoy it and that it proves to be instructive. As always, please do comment below. I welcome all feedback. And if you like this video, why not click on the like button and subscribe to the channel? If you feel like supporting my work, do take a look at the description of this video, where I've put the links to my Subscribestar page and my PayPal direct link. Thank you, and you can expect part 5 of this course next week.